Finally, for this week, we'll talk about strategies for dealing with the high memory requirements of medical imaging data, specifically patch-based training and alternatives to batch norm. The first and hopefully most obvious point is that you will need to move from applying 2D convolutions, as we've done in our previous examples, to using 3D convolutions. Here, the kernel size, stride, and padding may therefore be represented by integers or 3D shaped tuples. To understand then what the convolutional weights tensors are learning, it helps to go back and visualize the 2D convolutional operation again. But this time, rather than considering each filter operation of a 2D convolution as 3D with spatial dimensions of f by f and depth d for iteration L-1, where the depth corresponds to the number of channels of the incoming activation tensor, instead let's consider each filter as learning a stack of 2D kernel operations, as shown here in red, green and blue to represent the first convolutional layer operating on a 3-channel RGB input. The final activation output from the convolutional operation is therefore given by summing the activations observed from each of the individual 2D kernels. And this operation will then be repeated dl times once for each filter learnt by convolutional layer L. Thus, in 3D, the kernel operations themselves move to 3D, so as to operate within all 3 spatial dimensions of the image, and each filter learnt by a given 3D convolutional layer learns a stack of 3D kernels, each operating on different channels of the incoming activations, which themselves are each 3D. Then, as before for 2D, each 3D convolutional layer will learn dl of these filters. So 3D filters allow us to process 3D images, but processing stacks of 3D activation kernels requires optimization of many more weights than we needed previously for 2D. So how can we reduce the number of parameters that must be learnt in order to also reduce the chance of overfitting? Well, one thing we can do is instead train dilated convolutions which support learning distant contextual information in order to cover a comparable receptive field of multiple layers of regular convolutions and map pools in just one step without loss of resolution through downsampling. The next big issue is fitting 3D medical images in GPU memory to support training in the first place. So one way to deal with this is to instead process patches or slices of data at a time, where for certain tasks the selection of patches may be weighted to oversample classes with fewer samples, as we previously discussed in the context of dice losses. While memory constraints grow less and less as GPUs increase in size and memory, this technique remains popular as it also offers benefits in terms of varying the way the data is presented to the network, thereby acting as another level of data augmentation. There are various ways to approach patch-based training. One way originally proposed was to train 3 networks, each on 2D slices in the X, Y, Y, Z and ZX planes, where these are subsequently merged after the last layer of each network through a softmax classifier in order to make a final prediction. 3D context, however, can be highly relevant to certain types of object recognition and segmentation problem. So another approach that was proposed was to instead present the network with small stacks of 2D slices. However, a more typical approach nowadays is to crop isotropic 3D patches from whole images and train on them, where we will work to code up our own random patch sampler during the tutorial. And note that whole image contextual information is very important for many prediction problems, so it pays to make the patches as large as possible. However, of course, this then creates a trade-off against memory and batch size. Note, while patch-based training has predominantly been utilised for training segmentation networks, it can also be used for classification or, in the medical context, phenotype prediction. For example, one way to do this is to train patch-based classifiers to return a per-patch classification, and then to make a final prediction by fusing the results together as shown for this cancer detection approach based off histological slices. These types of images are extremely high resolution, making whole slice training prohibitive. However, by making predictions on parts of each slice, a stacking or ensembling approach can then be taken to return an image-wide per patient prediction. And while this might be understandable for histology, where strong evidence of cancer anywhere means a cancer diagnosis, this type of method can also be used for more diffuse and multi-system neurological disorders such as Alzheimer's. Thus, summarising the approaches for constraining network memory through downsampling, patch or slice-based training, there are several options ranging from downsampling, which will provide whole image context but at the cost of smoothing away small features, to 3D patch-based training, which presents full 3D context at high resolution but can be very memory intensive. In between, one might try slice-based training, however medical problems typically require full 3D information. The surface of the brain, for example, is highly variable and difficult to compare between subjects slice by slice. One tends to need to know where a region is in relation to other structures, viewed in all directions. To an extent, training on blocks of slices or merging slice-based predictions might mitigate this slightly, but at the same time you also stand to introduce a form of bias as you have one dimension along which the processing is slightly different. This makes it difficult to generalise to stacks from different orientations. Thus, typically these latter types of approach are much less often used. So let's say for argument's sake that we choose to train with large patches, or we have access to a large enough GPU to squeeze on whole images. In that case, we're presented with a new problem since we can no longer train with batch normalization, since our estimates of variance become unreliable or worse, zero if we're pulled down to a regime of training on a single example each time. So this is a problem because we know batch norm accelerates training, which will already be slow for training on large images, patch-based or not. At the same time, batch norm stabilizes or smooths the loss, thereby potentially leading to better convergence and as such generalization. Several variants have therefore been proposed which support normalization without batches. These include layer norm, which instead of normalizing across batches, normalizes across the features, otherwise known as the channels. So in doing so, it assumes that all these channels are equally important, which may not be true for typical CNN training. It's more often used for recurrent networks. Next is instance norm. This normalizes within channel but across activations in that channel in order to make the network contrast agnostic. This has been used successfully, for example, in style transfer generative models. Finally, for this diagram anyway, we also have group norm. So this instead considers groups of channels and normalizes across these. It can be seen as a combination of instance and layer norm without assuming that all channels have equal importance. Performing operations across groups of channels is not unusual and actually is increasingly common for networks seeking to conserve memory, for example, MobileNet. The authors also point out that traditional feature detectors such as SIFT and HOG also pool across features. And they trained group norm on traditional problems such as ImageNet classification using ResNets and showed that it outperformed batch norm for small batch sizes such as 2 and performed comparably well for large batch sizes. These are not the only options. Some other variants include batch renormalization, which estimates mean and variance as a moving average. However, the performance of this technique still degrades as batch size decreases, although not as quickly. Batch instance normalization, which normalizes difference in contrast and style of images. However, erasing discriminative style information such as brightness may not be what you want for medical images, where changes in image intensity over time can show properties such as tissue maturation and degeneration. And switchable normalization, which estimates the weighted average of different mean and variance statistics estimated for each of batch normalization, instance normalization, and layer normalization. On the other hand, a slightly different approach, which is also worth mentioning, is fix-up initialization, which instead of normalization layers redesigns the network initialization in order to initialize the classification layer and the last layer of each residual branch to zeros, and to initialize all other layers in a standard way but scale weights based on depth. The approach then estimates a scalar, multiplier, and bias parameter, which it adds to each residual layer, as does batch norm. They motivate this through extensive experiments looking into the interaction between weights initialization and training of very deep residual networks, where they show that through making the proposed changes, they can fully stop gradients vanishing or exploding even for networks of 10,000 layers. And talking of network initialization, in the first lecture we mentioned that weights of deep networks cannot be initialized to 0 and therefore must be initialized to small random numbers. However, taking such a simple approach can still lead to vanishing gradients as shown in the plot here. Therefore, bespoke initialization schemes existed way before fix-up, and these were all designed by exploring weights variance across layers. I believe PyTorch uses Xavier initialization by default. So, in summary, when moving to medical image problems from networks designed for natural image segmentation, the first thing we need to do is move from 2D to 3D convolutions, where here each filter learnt at a particular layer will be learning a stack of 3D kernels. Doing this is very memory intensive and parameter hungry, which can be a problem at the best of times, but we're dealing with very small data sets. So techniques for compensating for this therefore include use of dilated kernels and patch-based training, where it is typically recommended to take large 3D patches, where then this size will have to be traded off against batch size. Patch-based training has the added benefit of indirectly performing data augmentation. However, a limited batch size means that traditional batch normalization will no longer work, and this is a problem since it has been shown that it regularizes and prevents gradients from vanishing or exploding, especially for very deep networks. So if you cannot perform batch normalization, we recommend you looking at some alternatives. These include techniques such as layer norm, instance norm, or group norm, and also fix-up, where you may need to be careful to consider whether the approach would make sense in the context of your problem. Of these, I've heard of instance norm and fix-up used for medical image problems, and the group norm method seems well validated for natural image classification problems. So that's it for week 3. We will go on to practice some of these techniques in the tutorial.